Hello there, welcome to your tutorial on LeNet-5, one of the pioneering convolutional neural networks designed for handwritten digit recognition. In this video, we'll walk you through the architecture of LeNet-5, demonstrate how to implement it in Python, and show you how to train the model using Azure ML. Before we begin with anything, I really want to take some time to talk about the significance of LeNet-5. LeNet-5 is like the hello world in the domain of CNN. That's convolutional neural network. LeNet-5 is a gradient-based learning algorithm which was introduced in 1998, and it uses backward propagation, which was first introduced by itself in 1989, to solve the very popular problem or dilemma of the time, that's stochastic gradient descent, where the computational or the compute and the algorithm are in a stalemate and was for a long time thought to be an unsolvable problem. And it is thanks to LeNet-5 that we have deep neural networks as we know it today. It was LeNet-5 that proved that it was possible to build and train models with layers and layers of depth. And that is what we have, or we know it today as neural networks, deep neural networks. So to sum it up, LeNet-5 is the foundational step in the direction of deep neural networks, and it demonstrated that it's possible to build depth in neural networks, convolutional neural networks, and for that it used back propagation in its gradient based learning. Now let's talk about the architecture of LeNet-5 model. So if we exclude the input layer, we are left with 7 layers which comprises LeNet-5. 3 of them are convolutional layers, which are basically kernels or filters that perform the mathematical convolutional operation. And let's skip the details. You can look that up on convolutional operations in mathematics. Then we have 2 subsampling layers, which basically are used to reduce the dimensions of the image. And why do we want to do that is we want to reduce the computational complexity, because there are a lot of pixels and we do not just want to compute brainlessly, we do want to reduce our sampling size. We do call it in image processing the process of downsampling, and that's what we do to reduce the cost of computation. And then we have the fully connected networks, whose role is to learn the complex patterns and make the predictions. That's the output. So we usually train our models on a huge data set from MSIT, that's the standard, and it consists of lots and lots of handwritten training data for dataset. So this is an example of how LeNet 8 works visually. If we were to do so, we have layer 1, 3 and 5 as the convolutional layers, layer 1 being the input. We are able to understand human in a human manner, that it's the number that we are passing. But as you go into depth, layer 3 and layer 5, the details that are extracted from the neural network are more computational and it stops making sense for us. Chalo, now let's get hands-on experience on LeNet-5. Before we do that, there is a prerequisite, and that's that you have your workspace ready in Azure Machine Learning Studio. And in case you do not have it, there's a link in the description for a video which you can check out to set up your workspace. It hardly takes 15 minutes, and the video is hardly 6 minutes. Go through it and set it up, and you are ready to do the exercise with me. So I'm going to assume that you have it ready. So first of all, we need a compute on which we want to perform the machine learning or training of the model. So in the compute, I already have my compute ready, and it's a GPU with this specs. You can also create this by clicking on new, select GPU, and you can select anyone. I'm sticking with a very cheap one, but you can, according to your needs and your credit, of course. You can schedule, and actually once you schedule, it's their option. You can just review and create the resource for yourself. So I already have that, so I'm not going to do that. So now we will head to notebook in authoring section, and here We will create a new file, and that's going to be a Python notebook. So now I'm going to be very considerate about you and ensure that you have a good experience while you follow along with this video. So I'm going to show you that the library that I have on my system. So for this exercise, we will need Torch library from Python and also Torch Vision. So first of all, let's import sys and check the environment that this notebook is running on. And to do that, we can just import sys in Python, and sys stands for system, and then we can just print sys dot executable, and that will show us the environment that this notebook is picking. So this is the environment, and now I'll go to terminal from here. So let's make sure we are on the right compute. If you have multiple compute, you just want to click on this drop down and select your compute. So I'm going to check first of all the list of environments that exist on this compute. So the command for that is conda env list. So we have 5 to 6 environments showing up, and Jupyter Notebook is this one, but are we using this? Let's double check it with what we got on our notebook. So we are having SDK v2, and that's not this, surprisingly. We have this right here. So we are currently on Azure ML Pi 3.0, and we want to move to Azure ML Pi 3.10 SDK v2. So let's pick this up, and the command to move to this environment is conda activate followed by the environment that we just copied. So now here it shows that we have successfully moved to the environment we wish to move, and since we are now in this environment, we can make the library changes. So it's very naively it's a naive mistake to pip install the library in the default environment, and it's not being reflected, and you are scratching your heads what's happening. So now that we are in that environment that notebook is running on, we can just make sure that we are installing Torch and Torch Vision. For me, it's already installed on my environment in this compute. For you, it will be the first time, and it will actually install it. For me, it's just showing that requirement already exists, so it's not installing. Let's go ahead and install Torch Vision as well, and we'll get a similar already installed response, and that's there. So now let's head back to our notebook and put in the base code that's required. So I'll just paste it, and the code is all about fetching the MNIST data set and splitting it into training and testing data sets so that we can actually train our model and then test how it's performing and evaluate it, give it a score. So that's all being done here. We have downloaded all the data, and it has handwriting from all over the world, and it's a huge data set, and some of them frankly are really difficult for even me as a human to identify. But let's see how our model does. So we do need to refresh our directory if we are expecting some new folders or files. So let's see. There's a data folder, MNIST, and then we have we have images in compressed format. Let's not disturb that. So we are going to now define our LeNet-5 model in this section, and to do that, the approach for the video will be I'll just paste the code and explain what I have written, or it's pretty much very standard. What we are doing is we are just coding the picture of the architecture in this section. So from the picture we have input as 32 cross 32, then we have the convolution with 6 feature maps of 28 cross 28, and then next we have 6 feature maps of 14 cross 14, and so on. We have the layers. So if we focus on layer 1, we have neural network nn.convolution 2D. So we are performing 2D convolution, and we have 1 comma 6 comma kernel size equal to 5, stride equal to 1, padding equal to 0. So stride is the movement of kernel will be by 1 pixel and padding will be 0. So on the borders, we are not excluding any pixels. This is the first convolutional layer with 6 feature maps. That's what 6 is, and kernel size equal to 5 is that we are keeping it 5 cross 5. So interestingly, you might be thinking why the kernel size is 5 cross 5 and not 32 cross 32, or not 28 cross 28. In the next convolutional layer, we have 2 cross 2 kernel size, and then again we have 5 cross 5. What's happening? Well, the thing is that the way kernel size is the operation we are performing, so we are having 6 kernels of 5 cross 5, which will on acting on top of 32 cross 32, which is the input image, will make the output as size of 28 cross 28. And when 28 cross 28 is fed to 2 cross 2 kernel size of 6, 6 of them, it will become 14 cross 14. And how it happens, I'd love to show that, but let's not do it here. It's related to the operation of convolution in mathematics again. Other than that, we also have tanh, which is the activation function. So we have tanh curve, which we use to either activate or meaning just we want the output as 1 or 0, decisive, how confident you are, and we convert the value to 1 and 0 using the activation function right now as tanh. And for output in the very last layer, we will be using softmax, which is very popular for its implementation on the output. Specifically, we implement it softmax function, which is a mathematical function, as activation function in lots of machine learning models. It has its significance and background, which we will skip. Sorry, but that's the model that we have, and now we can proceed and go ahead to train and test them. So again, I'm just going to pick up the code that I have already written on my local and drop it on the notebook and execute it. So this will take some time, and let's run it. The first thing that you should observe is that CPU is going to go from 0 to 100% usage, and that's because computation of training of these models is really complex. If you don't feel like it's just the hello world of machine learning, CNN, go ahead and try it on your local. You'll see your local heating up and all the fans getting warmed up. You can also try on Google Colab, and you'll see it's much slower than what we have here on Azure ML Studio. The reason being we have a strong compute supporting this notebook, and we can always use a stronger compute. We have the option, right? We right now are using a very standard compute with standard GPU, but you can always go for more expensive ones which are much more powerful, and that's not the limit there. You can right now we are using compute instance. You can use compute clusters, which are basically a cluster of compute, and then train really complex models on your own, sitting at home, which you couldn't not have imagined before this without this platform. So specifically, if you are into training complex models, which could be related to image processing models like single image, super resolution, this is the platform that really empowers you. So basically what I'm trying to say is I really love this platform. It really empowers me to try out my own models, train them, which I would not have thought possible without at least not sitting at home and paying nothing. So it comes with a trial version where I can test things out and see if it feels good. But since this training is taking time and we are seeing epochs, let's talk about what's happening on the screen. So epoch is like we train the model on a data set, training set from input to output, and then we have back propagation algorithm, which comes back and retrains the weights, and with the complete training over, we have the value of the weights that we obtained from feedback. And after the epoch, we actually update the weights and then train again, make those weight changes, train again, make those weight changes, and that's basically building a stronger, more accurate model. And we have the score of 98.78% accuracy, and that's great. And with that, thank you for joining me on this video. I hope you learned something. If you did, do give this video a thumbs up and subscribe for more such content. Thanks and have a good day. Bye-bye. Up next, you can check out another fun video about where we are basically comparing Azure ML model training experience with the Google Colab and see the differences in terms of compute performance.